Hello, in this lecture we will find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle. We know that side AO equals to 6 units. Side AC is tangent to the semicircle at this point, and we want to find out the length of side AC that is equal to X. So we'll start with the first method, and we will define the center of this semicircle as P. Point P is the center of the semicircle, and we will define the point of tendency of tangent AC with this semicircle as D. Again, point D is the point of tendency of tangent AC with this semicircle. And here, because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle, and this angle OAB must be equal to 90 degrees. So, point O is the center of the quarter circle. Point A is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, AO is the radius of the quarter circle that is equal to 6 units. So, the radius of the quarter circle equals to 6 units. Therefore, here OB will be also the radius of the quarter circle. Why? Because it starts from point O, that is the center of the quarter circle, and ends at point B, that is a point of the quarter circle itself. Therefore, OB is the radius of the quarter circle, that is to say it is equal to 6 units. So, OB is the radius of the quarter circle, but OB is also the diameter of the semicircle. So we know that the diameter of the semicircle OB is 6 units. Therefore, the radius of the semicircle will be equal to half of it. That is to say, the radius of this semicircle equals to 6 over 2, that is 3 units. So OP equals to 3 units. PB also equals to 3 units. And here, PD will be also equal to 3 units. All those 3 line segments are defined as the eye of the semicircle. Why? Because they start from the center of the semicircle, that is to say from point B, and end at any point on the semicircle itself. And this is exactly the definition of a radius. So OP equals to PD equals to PB equals to 3 units, that is the radius of the semicircle. In the next step, we'll join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. I write it down. The lengths of two tangents from a common external point to a circle are equal. So I read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have also point P, this is point P is an external point of this circle, Y point P is an external point of this circle because point P is not located inside this circle nor on this circle but is located outside the circle, therefore point P is defined as an external point of this circle. So if the external point P, we will draw two tangents to this circle. The first tangent this is the first tangent to this circle. We define the point of tendency of the first tangent of this circle as point A. So PA is the first tangent. Then we will draw second tangent to this circle. We will define the point of tendency of the first tangent in this circle as point B. So PB is the second tangent. And according to rule number 1, the length of two tangents, that is to say the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the length of two tangents from a common external point, the common external point is point P, to a circle, 2 points A and B are equal. That is to say, PA is equal to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point of that circle, then the length of those two tangents will be equal to each other. In this case, PA equals to PB. Okay, so you can implement rule number 1 in our drawing. But in our drawing, we have the common external point, point A. From the common external point, point A, we have two tangents to this semicircle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, AO equals to AD according to rule number 1. So I'll write it down. According to rule number 1, AO equals to AD. Okay, but according to what is given us in the question, AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD. We will derive that AD is also equals to 6 units. AD is also equals to 6 units. So I can write here that AD equals to 6 units. In the next step, we will prove that those two right triangles, triangle AOP and triangle APD, can relate to each other according to side rule. Okay, so we'll prove that this triangle will prove that the right ring triangle, triangle AOP, this triangle, can orient to the right ring triangle, triangle APD, this triangle, according to side rule. Okay, so write it down. We'll prove that the right triangle, triangle AOP, congruent, this is the sign of congruent, to the right triangle, triangle APD, according to side rule. Okay, so why those two right ring triangles can relate to each other? First of all, we just right now found out that AO equals to AD equals to 6 units. According to rule number 1, AO equals to AD equals to 6 units according to rule number 1. In addition, side AP is a common side that belongs to both triangles. So AP equals to AP. AP equals to AP is a common side that belongs to both triangles. And finally, side OP equals to side PD equals to 3 units. Both those two line segments are the radii of the semicircle, so OP equals to PD equals to 3 units. So actually, all the 3 sides of triangle AOP can want all the 3 sides of triangle APD. Therefore, we can conclude from it that those 2 angles are equal to each other. Those 2 angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those 2 right triangles can go into each other, therefore those 2 corresponding angles must be also equal to each other. That is to say, angle OAP equals to angle PAD. And if we define angle OAP as theta, even OAP equals to theta according to our definition. So from this equation, theta equals to angle OAP equals to angle PAD, we derive that, that angle PAD is also equals to theta. So this angle PAD is also equals to theta. So both those 2 angles are equal to theta. In the next step, we will focus on the right main triangle, triangle OAP. On the right, green triangle, triangle OAP. This green right triangle, triangle OAP. We know that times theta equals to OP over OH. I repeat again. The right triangle, triangle OAP. Times theta equals to OP over OH. Here OP equals to 3 units and OA equals to 6 units according to what is given us in the question. So times theta equals to 3 over 6. Here we will divide both the numerator and the denominator on this side of the equation by 3. And we get that 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that times theta equals to 1 half. Times theta equals to 1 half. Times theta equals to 1 half. Okay, and in the next step we will join points O and C together by a straight line. And then I will introduce you the law of cosines, and we will implement the law of cosines in this triangle, triangle OSC. So what is the law of cosines? The law of cosines is true in any triangle So if we have triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB of this triangle, triangle ABC, equals to A units in its length. Side AC equals to B units in its length. And side BC equals to C units. And we also know that the angle between side AB and side AC is alpha. Then, according to the law of cosines, C square equals to A square plus B square minus 2 times A times B times cosine alpha. Okay? I'll repeat again. In this triangle, triangle ABC, this will be any triangle. C square equals to A square plus B square minus 2 times A times B times cosine alpha. Okay? Now we will implement the law of cosines in triangle AOC. So I copy triangle AOC in this page and we will implement the law of cosines in triangle AOC. We know that AC equals to x units according to what is given as the question. What is the length of side OC? O is the center of the quarter circle. C is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. And angle OAB equals to theta plus theta, that is 2 theta. So this is triangle AOC. Is a copy from the original drawing. Side AO equals to 6 units, side OC equals to 6 units also, and side AC equals to x units according to what is given as the question. And angle OAB equals to angle OAC equals to 2 theta. So according to the law of cosines, we'll get that this will be equation number 1. OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Okay. I repeat again, according to the law of cosines, OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Okay? So here, OC equals to 6 units, therefore OC square is 6 squared, that is 36. And it is equal to AO square. AO equals to 6. So AO square is 6 squared, that is also 36. Plus AC square. AC equals to x, so AC square will be equal to x square. Minus 2 times AO is 6 times AC is x times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And what is left of equation number 1 after we cancelled 36? In this side of the equation we have 0. That is equals to x squared minus 2 times 6 is minus 12. So this expression equals to minus 12x times cosine 2 theta. Here we will add to this equation number 1, 12x cosine 2 theta, and we get that according to equation number 1, 12x cosine 2 theta equals to x squared. Here we divide this equation number 1 by x. The reason that it is allowable to divide this equation number 1 by x, because x, it is equal to AC, it is a length, and as a length, x must be a positive number, it can never be equal to 0. For that reason, it is allowable to divide this equation number 1 by x. Okay? So here, x over x is 1, so in this side of equation number 1, we have 12 cosine 2 theta. For f times cosine 2 theta, and in the other side of equation number 1, x square over x is x. In conclusion, according to equation number 1, we found out that 12 times cosine 2 theta equals to x. So the only thing that is left to do in order to find out the length of line segment x, the line segment that we are looking for, is to find out the value of cosine 2 theta. So in order to find out the value of cosine 2 theta, I will present to you trigonometric identity for cosine 2 theta. According to the following trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 minus tangent square theta. Okay. And we already found out that tangent theta equals to 1 half. So we can substitute tangent theta in this trigonometric identity by 1 half. We'll do it now and we'll get that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1 half, therefore tangent square theta will be equal to 1 half squared over 1, here it is plus, 1 plus tangent square theta. Tangent square theta equals to 1 half squared one half squared is 1/4, so I write it down. We found out that cosine 2 theta equals to 1 minus 1/4 over 1 plus 1/4. Okay, so actually we found out that cosine 2 theta equals to 1 minus 1/4 is 3/4 and 1 plus 1/4 is 5/4. So in conclusion, we found out that cosine 2 theta equals to 3/4 over 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And what is left from this side of the equation after cancelled 4, what is left is actually 3/5. So cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. We'll do it now, and here we have equation number 1. According to equation number 1, 12 times cosine 2 theta equals to x. So here 12 times cosine 2 theta is 3/5. So we substitute cosine 2 theta in this equation number 1 by 3/5. And it is equal to x. So according to equation number 1, 12 times 3 is 36. So this side, in this side of the equation we have 36 over 5. That is equal to x. That is to say, according to equation number 1, x equals to 7.2 units, because 36 over 5 is 7.2 units. So x it is equal to AC, it is equal to 7.2 units. So here we found out that x that is equal to AC is equal to 7.2 units. We finish with the first method. In the next step I will present to you how to find out the length of line segment AC that is equal to x according to the second method. Okay. In the second method, we use all the things that we already found out in the first method. So here the center of the semicircle is P. The point of tendency of tangent AC with this semicircle is D. We have already found out that O is the center of the quarter circle. Angle AOB equals to 90 degrees. The radius of the quarter circle is 6 units. And the radius of the semicircle equals to 3 units. So OP equals to PB equals to DP. All those line segments are the radii of the semicircle, that is equal to 3 units. We joined points A and B together by a straight line in the first method, so we'll do it here also. And we already found out that triangle AOP can go into triangle APD according to side rule. And from the fact that those two triangles can go into each other, we concluded that those two angles are also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is equal to theta, the other angle must be also equal to theta because of the fact that they are equal to each other. So all those things we have already done in the first method. In this second method, we will do another construction. We will extend line segment AC and line segment OB by a straight line until they intersect with each other. And we will define the intersection point between the extended line segment AC and the extended line segment OB as E. E is the intersection point between the extended OB and the extended AC. Okay, so actually by doing this construction, we created the right triangle, triangle AOE. In this right triangle AOE, line segment AP bisects angle OAE, that is to say, it divides angle OAE into two equal parts. Each part equals to theta, to two equal angles. Each angle equals to theta. That is to say, this is the definition of the angle bisector. That is to say, line segment AP is the angle bisector of triangle OAE. For that reason, we can implement the angle bisector theorem in this right triangle, triangle OAE. So I present to you the angle bisector theorem, the meaning of the angle bisector theorem, and then we will implement the angle bisector theorem in this right triangle, triangle OAE. So what is the angle bisector theorem? The angle bisector theorem is true in any triangle. Angle bisector theorem so we can write down in any triangle in any triangle if we have triangle ABC, that could be any triangle. This is triangle ABC, and we also have line segment AD. Because of the fact that line segment AD bisects angle BAC, that is to say, it divides angle BAC into two halves, each half equals to theta. AD is defined as angle bisector of triangle BAC. Angle bisector. So right here that AD is angle bisector of angle BAC. Angle bisector. Line segment AD is angle bisector. Okay. So according to angle bisector theorem, we get that the angle bisector in a triangle in our specific case, the angle bisector is AD, so we'll enter it in brackets, that is, we are relating to line segment AD in triangle. In this case, we are relating to triangle ABC. I will write it down in brackets. Divides the side that it eats. In this case, The angle by sector AD eats side BC. Here. The angle by sector AD eats side BC and divides it into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. So divides the side it eats, divides the side that it eats in a ratio we already found out that the ratio that angle by sector AD divides side BC is BD over DC, so write down in brackets that it is actually BD, the ratio is BD over DC. In a ratio that is equal, that ratio is equal to the ratio between the angle's legs. We are relating here to the angle that has been bisected into two halves by the angle by sector AD. That is to say, we are relating to angle BAC. This angle BAC has been bisected by angle by sector AD into two halves. Each half equals to theta. So angle BAC, the angle that we are relating, has two legs. The first leg is AB and the second leg is AC. The ratio between those two legs is AB over AC. Okay? AB over AC. So the ratio between the angle's leg, that is AB over AC, equals to the ratio that angle by sector AD divides side BC. And that ratio is equals to BD over DC. Those two ratios, they are equal to each other according to angle by sector theorem. That is to say, AB over AC, that is the ratio between the angle's legs, equals to BD over DC, that is the ratio that angle by sector AD divides side BC. So, in conclusion, according to angle by sector theorem, in triangle ABC, with the angle by sector AD, AB over AC equals to BD over DC. Okay? So we can implement the angle by sector theorem in triangle AOE, because in triangle AOE we have AP that is the angle by sector. Here side AP is the angle by sector of the right triangle AOE, so we will implement the angle by sector theorem on this right triangle AOE. So I will copy the right triangle AOE in a new page and we will implement the angle by sector theorem in this right triangle, triangle AOE. So this is the right triangle, triangle AOE that I copied from the original drawing. Side AO equals to 6 units according to what is given as the question. OP is the radius of the semicircle that is equal to 3 units. So, and we know that AP is the angle bisector of triangle AOE. Why? Because it bisects angle OAE into two halves. Each half equals to theta. We will implement the angle bisector theorem in this right triangle, triangle AOE. According to angle bisector theorem, the angle bisector AP divides the side that it hits side OE, and divides it into two parts. The first part is OP, and the second part is PE. And the ratio between those two parts is OP over PE, and that ratio equals to the ratio between the angle's legs. We are relating to the angle that has been bisected into two halves, that is to say, angle OAE. Angle OAE has two legs, AO and AE, and the ratio between those two legs is AO over AE. The ratio between those two legs equals to the ratio that angle bisector AB divides side OE, that is OP over PE. So question number 1 is the implementation of angle bisector theorem in the right triangle AOE. So here OP equals to 3 units, so we substitute OP by 3 over PE. AO equals to 6 units according to what is given as the question. So in conclusion, we found out that according to equation number 1, 3 over PE equals to 6 over AE. Here we will divide this equation number 1 by 3, and we will also multiply it by AE, and we will get that according to equation number 1, six over 3 equals to AE over PE. 6 over 3 is 2, so I write it down. Here, according to equation number 1, 2 equals to AE over PE. Here we will multiply this equation number 1 by PE, and we get that according to equation number 1, two times PE equals to AE, that is to say AE is twice as long as PE. So we define PE as A. PE equals to A according to our definition. So here P equals to A, and also in the original drawing, line segment PE equals to A according to our definition. So now we know that P equals to A, so we can substitute PE in equation number 1 by A. We'll do it now, and we'll get that according to equation number 1, AE equals to 2 times PE, and PE is A, so AE equals to 2A. A equals to 2A according to equation number 1. Here, AE, side AE equals to 2A according to equation number 1, so we write it down, and PE equals to A according to our definition. We will continue to focus on the right triangle AOE, and in the next step we will implement the Pythagoras theorem on this right triangle, triangle AOE. Okay? So, here I will copy the right triangle, triangle AOE in a new page and we'll implement the Pythagoras theorem on the right triangle AOE. We have already found out that A equals to 2A, AO equals to 6 units. What is the length of AOE? OE, from the drawing it is very easy to see that OE equals to 3 plus A. Again, OE equals to 3 plus A. So this is the right triangle AOE that I copied from the original drawing. We will implement the Pythagoras theorem on the right triangle, triangle AOE. Here, by PT is the abbreviation for Pythagoras theorem. This will be equation number 2. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AE, so the square of the hypotenuse is AE square. It must be equal to the sum of the squares of the perpendiculars according to the Pythagoras theorem. That is to say, it must be equal to AO square plus OE square. According to equation number 2. AE equals to 2A, therefore A square is 2A square, and it is equal to AO square. AO equals to 6, so AO square is 6 squared, that is 36, plus OE square. OE equals to 3 plus A, so OE square is 3 plus A square. So in conclusion, according to equation number 2, we found out that 2A squared equals to 36 plus 3 plus A square. Here we will open the brackets on both sides of this equation, equation number 2, and we will get that according to equation number 2, two A squared is 4A squared, that is equal to 36, plus 3 plus A square is 3 squared, that is 9, plus A square, plus 6A. (36 plus 9 is 45, so I write it down. 45 equals to 4A square plus 6A. Here we divide the equation number 2 by 3. First of all, we subtract A square from this equation, equation number 2. 4A square minus A square is 3A square, and that is equal to, here we have also A square. A square minus A square is 0, so it is, in this side of the equation, what is left is 45 plus 6a. Here we divide this equation number 2 by 3, and we get that according to equation number 2, 3a squared over 3 is a squared, and it is equal to 45 over 3 is 15, plus 6a over 3 is 2a. We will subtract 15 and also 2a from this equation number 2, and we get that according to equation number 2, a squared minus 2a minus 15 equals to 0. So here we have a quadratic equation. The missing variable in this quadratic equation is a, so here x equals to a. The coefficient a in this quadratic equation is equal to 1. The coefficient b is equal to minus 2. And the coefficient c in this quadratic equation is equal to minus 15. We put the data here. Actually, the general formula to solve a quadratic equation, the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now we put the data inside the general formula and we find out the value or the values of x, because here the missing variable is a, so x equals to a. So here we get that a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared. B equals to minus 2, so b squared is minus 2 squared, that is 4, minus 4 times ac, minus 4 times a is 1, and c is minus 15, so it is times minus 15 over 2a. A is 1, so 2a is 2 times 1, that is 2. So here we found out that a equals to 2 plus minus. Inside the root we have minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root what is left is only 64 over 2. So here a equals to 2 plus minus, the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that we're going to do the first solution for a equals to minus 3. That is a negative number, of course. But according to our definition, the length of a side PE of triangle APE equals to A. So A is the length of side PE, and A is a length, it must be a positive number. A is a length, and as a length, it must be a positive number. It can never be equal to minus 3, that is a negative number. So we'll cancel this solution, and we're left only with the second solution, that A equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A equals to 5 units. So we can write here that A equals to 5 units. That is to say, A that is equal to 3 equals to 5 units. So if A equals to 5 units, it means that 2A equals to 2 times 5, that is 10. That is to say, side A equals to 10 units, and side P equals to 5 units. So in the next step, we'll find out the length of line segment BE. So the length of line segment BE, from the drawing it is very easy to see that the length of line segment BE equals to PE minus PB. Repeat again, BE equals to PE minus PB. So BE equals to PE. PE is A, it is equal to 5 units, minus PB. PB equals to 4 units, it is the radius of the semicircle. So in conclusion, we found out that BE equals to 5 minus 3, that is 2. So BE equals to 2 units. In the next step, we'll find out the length of line segment CE. From the drawing, it is very easy to see that the length of line segment CE equals to AE minus AC. Again, AE minus AC equals to CE. So CE equals to AE minus AC, CE equals to AE equals to 10 units, AE equals to 10 units, minus AC, AC equals to X, it is the line segment that we are looking for. It is equal to X according to what is given us in the question. So in conclusion, we found out that AE and that CE equals to 10 minus X. AC equals to 10 minus X. And we can write down that CE equals to 10 minus X. And we have already found out that B equals to 2 units, so we can write here that B equals to 2 units. In the next step, we will extend the quarter circle to a circle. So we extended the quarter circle to a circle, and then we will extend line segment BO by a straight line until it touches the circle, and we will define the touching point of the extended line segment BO and the circle as M. So what is the length of line segment MO? The length of line segment MO, O is the center of the quarter circle, M is the point of the circle itself, and this is exactly the definition of a radius. That is to say, MO is the radius of the circle itself, that is also the radius of the quarter circle, that is to say MO equals to 6 units, because the radius of the quarter circle equals to 6 units, and it is also the radius of the circle itself that is also will be equal to 6 units. Okay, so in the next step I will present to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So I write it down. If two chords intersect with each other outside the circle, that is to say, the meaning of this sentence is that the intersection point of those two chords is happening outside the circle. The point of the intersection is outside the circle. So if two chords intersect with each other outside the circle, then the following equation is true. So actually, have here the external point P. Point P is the intersection point between those two chords. And we have chord AB. This is chord AB that intersects with chord CD at point P. I repeat again, chord AB intersects with chord CD at point P. Point P is the intersection point. I write it here that point P is the intersection point. Intersection point between those two chords, A, B and C, D. Okay? So, if chord AB intersects with chord CD at point P is the intersection point, then the following equation is true. That PA times PB PA times PB equals to PC times PD. I'll repeat on rule number 3 again. According to rule number 3, if two chords intersect with each other outside the circle, so we have here chord AB that intersects with chord CD outside the circle is point P. Point P is the intersection point between those two chords that and point P is located outside the circle. Then, according to rule number 3, the following equation is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. So actually, you can implement rule number 3 in our drawing. We can implement rule number 3 in our drawing. Why? Because in our drawing we have chord AC. This chord intersects with chord MB at point E. Point E is the intersection point between chord AC and chord MB. That is located, point E is located outside the circle. So all the conditions of rule number 3 are met. Therefore, we can implement rule number 3 in our drawing. Because of the fact that chord AC intersects with chord MB at point E that is located outside the circle, we can implement rule number 3, and according to rule number 3, EC times EA equals to EB times EM. Again, EC times EA equals to EB times EM. So write it down. In our specific drawing, we have chord AC intersects with chord MB, with this chord MB at point E. At point E, here point E is the intersection point between chord AC and chord MB, and point E is located outside the circle. So all the conditions of rule number 3 are met. I'll repeat again. All the conditions of rule number 3 are satisfied. Chord AC intersects with chord MB at point E. Okay? Therefore, according to rule number 3, EC times EA, EC times EA equals to EB times EM. I'll repeat again. Chord AC intersects with chord MB at point E. Point E is the intersection point. Therefore, according to rule number 3, we will get that the following equation is true, that EC times EA equals to EB times EM. Okay. So EC CE, okay, CE equals to 10 minus X here. EA equals to 10 units, and it is equal to EB equals to 2 units, and EM is the long line segment. EM equals to 6 plus 3 plus 3, that is 12, and 12 plus 2 is 14. So in conclusion, EM equals to, in total, EM equals to 14 units. So according to rule number 3, we found out that 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28, so I write it down. 28 equals to 10 times 10 minus x. Here we divide this equation by 10, and we get that according to this equation 10 minus x equals to 28 over 10 is 2.8. Here we will add to this equation x, and we will subtract 2.8, and we get that according to this equation x equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that x, that is actually also equals to AC, is equals to 7.2 units. So according to the second method, we arrive to the same result for x that is equal to AC. It is equal to 7.2 units according to the second method. Here x equals to AC, and it is equals to 7.2 units. Okay, in the next step I will summarize the lecture. We will start with the first method. So I repeat on the question. We have here a semicircle inside a quarter circle. We know that side AO equals to 6 units. Side AC is tangent to this semicircle at this point D. And we want to find out the length of line segment AC that is equal to x. According to what is given as the question, AC equals to x. So we want to find out the length of side AC that is equal to x. So we defined the center of the semicircle as P. We defined the point of tendency of tangent AC with this semicircle as D. And here, because of the fact that this is a quarter circle, then point O must be the center of the quarter circle. And also angle AOB must be equal to 90 degrees. Okay? So point O is the center of the quarter circle. Point A is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, AO is the radius of the quarter circle that is equal to 6 units according to what is given as the question. That is to say, the radius of the quarter circle is equal to 6 units. And for that reason, for the same reason, OB is also the radius of the quarter circle that is also equal to 6 units. But OB is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units. If the diameter of the semicircle equals to 6 units, it means that the radius must be equal to half of it, that is 6 over 2 is 3 units. So the radius OP that is equal to PB equals to PD, they are all the radii of the semicircle, and therefore they are equal to 3 units. Why? Because all those 3 line segments exist from the center of the semicircle and end at any point on the semicircle itself, and this is exactly the definition of a radius. That is to say, all those 3 line segments are defined as the radii of the semicircle, and for that reason they are equal to 3 units each. Okay, then we join points A and 3 together by a straight line, and then I presented to you a new rule that is actually rule number 1. According to rule number 1, the lengths of 2 tangents from a common external point to a circle are equal. So here we have this circle, and we have point P. Point P is an external point in relation to this circle, and from point P we draw two tangents to this circle. The first tangent is tangent PA, and the second tangent is tangent PB. And according to rule number 1, the length of two tangents, the length of the first tangent is PA. The length of the second tangent is BB. So the length of those two tangents from a common external point, the common external point is point P, to a circle, 2 points A and B are equal. That is to say, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB, according to rule number 1. So whenever you draw two tangents to a circle from a common external point to that circle, to a circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. We can implement rule number 1 in our drawing, because in our drawing we have point A. This is a common external point in relation to this semicircle. From the common external point A, we have two tangents to this semicircle. The first tangent is tangent AO, the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents must be equal to each other. That is to say, AO equals to AD. AO equals to AD according to rule number 1. But according to what is given as the question, AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. So here, AD, 9 segment AD equals to 6 units. In the next step, we proved that those two green right triangles can go into each other according to side rule. Here, why they can go into each other? Here we have side AO equals to side AD equals to 6 units according to rule number 1 that we just have already found out. And side AP is the common side that belongs to both triangles, so AP equals to itself. And here OP equals to PD equals to 3 units. It is the radius of the semicircle, so all the sides of triangle AOP can go into all the sides of triangle APD. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we conclude that those two angles are equal to each other. That is to say, angle OAP equals to angle PAD. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles they can go into each other, therefore those two corresponding angles must be also equal to each other. And if we define angle OAP as theta, then that is to say here angle OAP equals to theta, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. This angle PAD is also equals to theta. So both those two angles are equal to theta. Then we join together points O and C by a straight line. And I presented to you the law of cosines, and we implemented the law of cosines in this triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle ABC, that could be any triangle, side AB equals to A units, side AC equals to B units, and side BC equals to C units. And we also know that the angle between side AB and side AC equals to alpha. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times AB times B times A squared. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay, then we implemented the law of cosines in this triangle AOC. I copied the triangle AOC in this new page, and we implemented the law of cosines in this triangle AOC. Side AO equals to 6 units, according to what is given as the question, and side AC is the line segment that we are looking for. It is equal to x according to what is given as the question. What is the length of side OC? O is the center of the quarter circle and C is the point of the quarter circle itself. And this is exactly the definition of a radius. Any point that starts from the center of the circle, of the semicircle, of the quarter circle and ends at the point on the circle of the quarter circle itself is defined as a radius. So OC is the radius of the quarter circle that is equal to 6 units. OC equals to 6 units. Now we implemented the law of cosines in this triangle, triangle OC. Angle OAC, this angle OAC equals to theta plus theta, that is 2 theta. So we implemented the law of cosines in this triangle, triangle OC, OAC. According to the law of cosines, OC square equals to OA square plus CA square minus 2 times AO times AC times cosine 2 theta. Okay, OC equals to 6 units. Therefore, OC square is 6 squared, that is 36. OA equals to 6 units. Therefore, OA square is 6 squared, that is also 36. And it is equal plus AC square. AC is x, so AC square is x square. Minus 2 times AC is 6. Minus 2 times AO, that is 6, times AC, that is x. Times cosine 2 theta. So here we have 36 on both sides of the equation, so 36 will get cancelled, and we left only in this side of the equation number 1, 0, that is equals to x squared minus 2 times 6 is minus 12, so this expression equals to minus 12x cosine 2 theta. So in conclusion, according to equation number 1, 0 equals to x squared minus 12x cosine 2 theta. We added 12x cosine 2 theta to this equation, equation number 1, and found out that according to equation number 1, 12x cosine 2 theta equals to x squared. Then we divided this equation, equation number 1 by x, and found out that according to equation number 1, uh, 12 times cosine 2 theta equals to x squared, because x squared over x is x. And here x will get cancelled, so we have only left with 12 times cosine 2 theta, and here x squared over x is x. So in conclusion, we found out that 12 times cosine 2 theta equals to x. So the only thing that is left to do here, in order to find out the value of x, the line segment that we are looking for, is to find out the value of cosine 2 theta. In order to find out the value of cosine 2 theta, I presented to you new trigonometric identity that cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. But we have already found out that tangent theta equals to 1 half, so we can substitute tangent theta in this trigonometric identity by 1 half. We did it, and we got that here cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1 half, it means that tangent square theta will be equal to 1 half squared. So in the numerator we have 1 minus 1 half squared over 1 plus tangent square theta, that is 1 half squared. Okay, 1 half squared is 1 quarter. So here we substitute 1 half squared by 1 quarter, and we will get that cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 quarter. 1 minus 1 quarter is 3 quarters. 1 plus 1 quarter is 5 quarters. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And after we cancel 4, what is left from this equation? What is left is only, in this side of the equation, what is left is only 3/5. So in conclusion here, cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. We did it. So here 12 times cosine 2 theta equals to x. Here, according to equation number 1, 12 times cosine 2 theta equals to x. And we substituted cosine 2 theta by 3/5. And we got here that 12 times cosine 2 theta is 3/5, that is equal to x. So in conclusion, we found out that according to equation number 1, x equals to 12 times 3 fifths. 12 times 3 is 36, so this expression equals to 36 over 5. So x equals to 36 over 5 according to equation number 1. That is to say, x that is equal to AC, it is equal to 36 over 5, and 36 over 5 is 7.2 units. So in conclusion, we found out that x that is equal to AC, it is equal to 7.2 units. Again, x that is equal to AC equals to 7.2 units. We finished with the first method, then I presented to you how to find out the value of line segment x according to the value of line segment x according to the second method. In the second method, used before the things that we already found out in the second method. In the second method, used before the things that we have already found out in the first method. So here, point B is the center of the semicircle, point O is the center of the quarter circle, and the radius of the quarter circle is 6 units. The radius of the semicircle is 3 units. So OP equals to PD equals to PB equals to 3 units. That's the radius of the semicircle. Those two triangles can go into each other according to side rule. Therefore, from the fact that those two triangles can go into each other, we will derive from it that those two angles will be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is equal to theta, then the other angle will be also equal to theta. So those two angles are both equal to theta. So until this stage, until this step, we did all things in the first method. And here in the second method, we did another construction. We extended line segment AC by a straight line, and we also extended line segment OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended AC and the extended OB. So in this way, we created the right triangle AOE. The right triangle AOE, we have PA, that is angle bisector. Why PA is angle bisector? Because it divides angle OAE into two halves. Each half equals to theta. For that reason, PA is angle bisector. So we can use the angle bisector theorem in the right triangle OAE. So, but first of all, I presented to you what is exactly angle bisector theorem. So here we have triangle ABC, that could be any triangle. AD is angle bisector. Why? Because it divides angle BAC into two halves. For that reason, it is angle bisector. So, according to angle bisector theorem, the angle bisector in this case is AD, divides the side that it eats. Angle bisector AD in triangle ABC eats side BC, so, and it divides it into two parts. Here, the first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. Okay? So the angle bisector AD divides the side that it is BC in a ratio that is equal to BD over DC. And that ratio is equal to the ratio between the angles legs. We are relating to the angle that is been bisected into two halves. That is to say, angle BAC. And angle BAC has two legs. The first leg is AB and the second leg is AC. And the ratio between those two legs is AB over AC. And that ratio, AB over AC, equals to the ratio that angle bisector AD divides side BC. That is to say, it is BD over DC. So in conclusion, AB over AC equals to BD over DC. Okay, so, then we implemented the angle bisector theorem in the right triangle, triangle AOE. In the right triangle, triangle AOE, OP is the radius of the semicircle, that is 3 units. Here, we have PE equals to A according to what is given as the question. So here the angle bisector AP in the right triangle AOP divide side OE into two parts. And the ratio between those two parts is OP over PE. And that ratio equals to the ratio between the angles legs. We are related to angle OAE. Angle OAE is two legs, AO and AE. And the ratio between those two legs is OA over AE. The ratio between those two legs, that is OA over AE, equals to the ratio that angle bisector AP divides side OE. That is actually equals to OP over PE. Okay, those two ratios are equal to each other. The ratio that angle bisector AP equals divides side OE is OP over PE, and that ratio equals to the ratio between the angles legs, that is OA over AE. So those two ratios are equal to each other. That is to say OP over PE equals to AO over AE. OP equals to 3 units, so we substitute OP by 3. So it is 3 over PE equals to AO equals to 6 units according to what is given as the question, so it is 6 over AE. We divided this equation by 3 and we multiplied it by AE, and we got that 6 over 3 equals to AE over PE. 6 over 3 is 2, so we wrote here that 2 equals to AE over PE. We multiplied this equation by PE, and we found out that 2 times PE equals to AE. We defined PE as A, so here PE equals to A according to our definition. Here also PE equals to A according to our definition. So if PE equals to A, then from equation number 1, we can substitute PE by A in equation number 1. So A equals to 2 times PE, and PE is A, so AE equals to 2A. So according to equation number 1, AE equals to 2A. Okay? Then, so we know that P equals to A and AE equals to 2A. Then we continue to focus on the right triangle OAE, and we implemented the Pythagoras theorem on this right triangle, triangle AOE. So I copied the right triangle AOE in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle AOE. This is the right triangle AOE. AO equals to 6 units according to what is given as the question. We have already found out that AE equals to 2A, and here OE, line segment OE equals to 3 plus A. Again, line segment OE equals to 3 plus A. So here OE equals to 3 plus A, so we implemented the Pythagoras theorem on this right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AE, so the square of the hypotenuse is AE square, and it is equal to AO square plus OE square. AO equals to AE equals to 2A, so we substitute AE by 2A. So if A equals to 2A, then AE square equals to 2A square, and it is equal to AO square. AO equals to 6, so AO square is 6 squared, that is 36, plus OE square. OE equals to 3 plus A, so OE square will be equal to 3 plus A square. Here, we open the brackets on both sides of this equation, equation number 2. 2A squared is 4A squared, and that is equal to 36, plus 3 plus A squared is 3 squared, that is 9, plus A squared plus 6A. Then we subtracted A squared from this equation, equation number 2, and found out that 4A squared minus A squared equals to 3A squared. So here, and A squared minus A squared is 0, so in this side of the equation, what is left is only 45 plus 6A. Here we divided this equation, equation number 2 by 3, and found out that 3A squared over 3 is A squared, 45 over 3 is 15, and 6 over 3 is 2A. So here we have A squared that is equal to 15 plus 2A. We subtracted 15 and also 2A from this equation, equation number 2, and found out that A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation. The missing variable is this quadratic equation. The variable that we are looking for is A. So x equals to 8, the coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b square minus 4 times ac over 2a. Here x equals to a, so we substitute x by a, and we found out that a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2 plus minus square root of b square. B equals to minus 2, so b square is minus 2 squared, that is 4. Minus 4 times a is 1, and c is minus 15, so it is minus 4 times minus 15 over 2a. A is 1, so 2 times 1 is 2. So in conclusion, we found out that a equals to 2 plus minus square root of minus 4 times minus 15 is 60, and 60 plus 4 is 64. The square root of 64 is 8. So here a equals to 2 plus minus square root of 64 over 2, and the square root of 64 is 8. So in conclusion, we got two solutions for a. A equals to 2 plus minus 8 over 2. The first solution is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a is a negative number, is minus 3. But here, according to our definition, a is the length of side PE of triangle APE. And a is a length, it must be a positive number. It can never be a negative number. So a can never be equal to minus 3. We cancel this solution, and we left only with the second solution. That a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So here we found out that a equals to 5 units, that is to say PE equals to a equals to 5 units. And if a equals to 2a and a equals to 5, that means that 2 times 5 is 10. So a equals to 10 units, and p that is equal to a equals to 5 units. Then we found out the value of line segment BE. From the drawing, it is very easy to see that BE equals to PE minus PB. B equals to PE minus PB. PE equals to A equals to 5 units. PB is the radius of the semicircle, that is 3 units. So B equals to 3 minus 5, that is 2. In conclusion, B equals to 3 units. Then we found out the length of line segment CE. CE, from the drawing, it is very easy to see that CE equals to AE minus AC. Again, AE minus AC equals to CE. Here, CE equals to AE minus AC. AE equals to 10 units, and AC equals to X. This is the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus X. Here, CE equals to 10 minus X, and then we already found out that B equals to 3 units. Then I presented to you a new rule, that is rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true, that PA times PB equals to PC times PD. So here we have chord AB that intersects with chord CD outside the circle at point P. At point P is the intersection point between chord AB and chord CD. So if this is the data that we have, then according to rule number 3, we will get that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. We can implement rule number 3 in our drawing, because in our drawing we have here chord AC intersects with chord MB at point E. Again, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC and chord MB. That is actually, of course, outside the circle. Therefore, all the things that rule number 3 requires are satisfied in our drawing, and therefore we can implement rule number 3 in our drawing. Okay, I'll repeat again. Chord AC intersects with chord MB at point E. Therefore, according to rule number 3, we'll get that EC times EA equals to EB times EM. Again, EC times EA equals to EB times EM. Okay, EC times EA equals to EB times EM, according to rule number 3, of course. EC equals to 10 minus X, EA equals to 10 units, EB equals to 2 units, and the big line segment ME equals to 6 plus 3 plus 3, that is 12. 12 plus 2 is 14. So in total, we found out that EM equals to 14 units. So 10 minus X times 10 equals to 2 times 14, according to rule number 3. 2 times 14 is 28, so here we found out that 10 minus X equals to 28. We divided this equation by 10, and found out that 10 minus X equals to 28 over 10 is 2.8. Then we added to this equation X, and we subtracted 2.8, and we found out that X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that X, that is equal to AC, it is equal to 7.2 units. So in both methods, we found out that the line segment X, that is equal to AC, equals to 7.2 units. Okay, thank you very much.